Can everybody? I think I'll just hold it. Is that okay? Everybody hear me? Okay, cool. So as Jessica mentioned, I'm a postdoc with USDA Ag Research Service in Columbus. But today I'm going to be talking with you about the work I did in grad school at Penn State on dairy slurry. And so to provide a little bit of context, Penn State is located in the Chesapeake Bay watershed, so I know everybody here is mostly focused on Lake Erie and the Western Lake Erie watershed. Similar problems, different watersheds. So I'll be discussing manure nutrients in the context of a TMDL that was implemented in 2011. And so it was essentially putting the bay on a nutrient diet, which is tricky considering all the states involved and all the agriculture involved with 64,000 square miles of land, all contributing to the bay. So based on model estimates, about 40% of the nitrogen reaching the bay can be attributed to manure or fertilizer. And so you can see the goal by 2025 to reduce nutrients by 22% is a pretty big goal, not unlike what we have trying to reduce nutrients reaching Lake Erie. And so this was a no-till project. It was part of a Northeast Sustainable Ag Research education grant, Northeast SARE, and we were conducting our small plot design at the Penn State Agronomy Farm. Here you can see a picture. The yellow is actually canola. The previous speakers were mentioning canola, so we were growing that actually to provide fuel and feed, fuel for our straight vegetable oil tractor, and feed for our dairy herd or our virtual dairy herd. So I was focused on the manure side of things. So how can we no-till apply nitrogen in this system that is not broadcasting? So we were looking at injection. On the right, you can see a picture of the toolbar that we are using. And on the left, you can see the broadcast application. And so we wanted to, with this manure study, understand the fate of nitrogen when we use these two different application methods. So where is the nitrogen going within the system, and how does it differ between the two treatments? And so the most common no-till, as you all are probably familiar with, is broadcast application. Just a quick overview. You can see the soil surface looks a lot different when you're spraying it out on top of the land. And so when you look at shallow disc injection, we're using a Yetter toolbar, 30-inch spacing, and we're about 4 inches deep, and there's closing wheels behind. So you can see in this little cartoon diagram, the coulter in the front cuts the soil, and then there are nozzles dropping the slurry down and closing wheels. So the odor is significantly decreased as well, and then the soil surface looks a lot different. You don't have manure just sitting, especially in Pennsylvania where there's a lot more topography than here, and we're worried about wash-off events. This was a big concern. No-till is a big deal, and so finding ways to get your poop on the land without tilling is crucial. And so for this study, I wanted to follow nitrogen in its different fates. So as we know, surface applying can lead to lots of ammonia volatilization. So I wanted to measure how much we were losing off of broadcast plots to compare that to inject. When you're incorporating, any kind of incorporation will dramatically decrease your volatilization. Conversely, when you incorporate, there's potential for nitrous oxide emissions and denitrification. So we were going to measure nitrous oxide, leaving the plots, and then the field setup that we had also allowed us to look at overland flow, so nitrogen moving over the plot surface, and then look at shallow lateral flow or subsurface flow. We were also measuring soil nitrogen, what was happening throughout the growing season, and crop uptake. So trying to capture as many pathways of nitrogen as we could, which is not an easy task. But today I'll be talking about sort of the setup, the study design on what we were calling field lysimeters. It's a unique study site that was built to look at water movement overland and subsurface, and then I'll move into what I highlighted previously in terms of nitrogen fate. So what we found in our emissions, nitrous oxide and ammonia volatilization, and then what we found in overland and subsurface flow, what were the soil dynamics, plant uptake, and then to wrap things up, I'll talk about the integrated farm system model that I used to scale up the research. So, as you can see, there's 12 plots. We had 2 treatments, so 6 of inject and 6 of broadcast. That's just a Google Earth view of the study site. And then this is what I meant by field lysimeter. So you can see in this cross-section diagram that we have each plot bermed so that we can capture overland flow. So anything in theory running over the surface of that plot is then routed through a series of PVC pipes down to collection houses at the base of the hill slope. And then at the base of each plot, then underneath those berms, there's tile lines, which everybody here is familiar with tile drainage. So basically we're capturing, ideally, anything moving through the soil profile at depth, and then monitoring that volume of water moving off of the plots. And we had a weather station, and anyway, so it was an ideal location to try and look at nitrogen and water movement. What we quickly realized was that there is some landscape variability, and I'll get into some of that later in the data, but this was a nice picture of the site. The green is definitely enhanced in this, but you can see at the top of the hill slope, as one might expect, there's shallower soil. We had droughty conditions a lot of the times during the summer, and so that corn didn't fare as well as the corn located in plots that had greater soil depth. And so with this variability, we thought, okay, well, we're trying to measure all the different pathways of water movement. Can we estimate a water budget for the site? So this was sort of all the preliminary work going into the first study done on whole field lysimeters. How are these plots behaving? And so clearly we're losing, even though it's supposed to be a closed system, we're losing through the bedrock and through other pathways a lot of water. And so there was approximately 22% of our unaccounted for water. Obviously, the great majority of what's happening at the site is ET, and then we had a large portion moving in shallow lateral flow. So the biggest measurable pathway that we had at the site was our shallow lateral flow, and then we had a little bit of water moving overland, but it was about less than 1% of the overall budget estimation. So that was sort of the preliminary work setting up the site. And so now I'll move into gas emissions. And so looking at volatilization, it's pretty well known, any kind of incorporation will reduce your ammonia loss, but our hypothesis was that because you're putting that manure, that's a high organic content substrate, essentially, deep into the soil, you're providing these microsites of anaerobic activity. So we're providing denitrifying microbes with a food source that could potentially create a greenhouse gas, nitrous oxide. And so that was the reasoning behind measuring nitrous oxide, because if we're decreasing ammonia volatilization, which is a particulate matter concern, are we creating a new problem by enhancing denitrification and nitrous oxide emissions? So that was the hypothesis. The top 2 photos are the chamber method that we used to measure nitrous oxide. So basically we went out about 4 or 5 days after manure application, set up these 30-inch square chambers, and then took syringe samples of air out of the chambers at different time intervals, and then ran those on a gas chromatograph in the lab. And then we had a photoacoustic gas analyzer that we used to measure ammonia volatilization, and that's the bottom 2 photos. So we followed the manure spreader around the field that day and for 2 days following to get these gas emissions. And so just to give you a brief overview of the data, our hypothesis that injection would significantly decrease ammonia emissions was proven, and also very well known from previous research at the same farm location. You can see by the 5-minute, 3-hour, 24-hour, 48 hours, by 2 days, we didn't have any more volatile emissions on either broadcast or inject. And the units on the y-axis you can see are in kilograms per hectare per day. So we can lose a lot in a short amount of time, lose a lot of nitrogen via this pathway. But to look at, this is a lot of graphs going on, but basically the top graph is the precipitation events that we had in the measurement time frame for nitrous oxide, and then the graph below it is volumetric water content. I have soil temperature, and then the bottom graph are the nitrous oxide emissions. And so whereas we were dealing with kilograms per hectare loss of nitrogen, with nitrous oxide it's on the scale of grams. So it's a much smaller pathway of loss. It's less agronomically significant, but is it environmentally significant was the question. About 7 to 10 days after manure application, we did see peaks in nitrous oxide, but that tapered off throughout the growing season. And so it was an interesting finding. There's not a ton of research on nitrous oxide, but I think it's growing. And so that was the motivation to measure nitrous oxide and see if it would be significant compared to broadcast. And again, just to kind of bring home the point that it's not necessarily significant agronomically speaking. So if you're worried about your nitrogen application, nitrous oxide would not be a major pathway of loss, and you can see that in the cumulative emissions here. So over that whole spring time period in 2011, 2012, we also had fall measurements in 2012 and spring 2013. You can see overall loss of nitrogen is not that great. So moving on to looking at what we found in overland flow and subsurface flow. So like I said, like cycling back to the plots, we were able to calculate how much water was moving overland by tipping buckets. And so here's a closer picture of that. We just had data loggers attached to those tipping buckets. It's kind of like an overgrown precipitation gauge, if you have a tipping bucket version of that. And so it's counting the tips. And then we were subsampling during events the water that was coming out of the bottom of the tippers. So we had one pipe that was monitoring our overland flow and another pipe for each plot that was monitoring our subsurface. Some water samples. And so to give a picture of, for the whole monitoring period from 2011 through 2014, there wasn't a treatment difference in overland flow. We would hypothesize that broadcast plots would produce more, would produce greater nitrogen loads because you're leaving the nutrient available for wash-off. There were some instances where maybe it was a little bit greater than injected plots, but it wasn't necessarily significant. Again, the units are kilograms per hectare per day of loss. And so we're on the like 0 to 6 sort of kilogram scale. So a fairly small pathway of loss, at least at this site. Whereas when we looked at subsurface flow, there were greater loads because there was greater amount of water moving through the soil profile. But interestingly and actually promising was that we didn't see a difference here either with treatment. So one would hypothesize that because you're putting that nutrient below the soil surface, you could be leaving it more vulnerable to loss via leachate. So nitrogen can move really easily through the soil profile, and nitrates in groundwater is always a big concern. We didn't see any evidence of that in these few years that we were monitoring, but it is a larger pathway of loss, at least at this site, because there's a larger volume of water moving through than overland. And just to give you a picture of what the data looked like on an annual scale, I have the treatments broken out by year, so broadcast and injection for 2012, 2013, and 2014. And on the y-axis, again, nitrate loads in kilograms per hectare. And so we were losing quite a bit in subsurface if we're on the 0 to 60 scale there, whereas overland it was the 0 to 1.5 or so kilograms per hectare loss of nitrogen. And so looking at what we found, some trends that we found in the soil and the nitrogen dynamics there. And so we're looking at the temporal difference between pre-manure and post-harvest. So April would have been pre-manure application, and September would have been just after corn silage harvest, which is what these plots were in, continuous corn. we can see that in the first year. So we would think, oh, we're conserving nitrogen by injecting it, by putting it under the soil surface, so maybe we'll see a bump in the nitrogen that we measure. And in the first year in September, we did see that. So the red bars are the injected plots, and at every depth, down to about 3 feet, we did see a significantly greater nitrate in injected plots as compared to broadcast. However, when we went back and did the same analysis for the 2013 growing season, we didn't see that same trend, but nitrogen can also be pretty fickle. It can move really easily. I currently study phosphorus, so nitrogen is a lot more difficult to measure in environmental systems. So there's potential for more like nitrogen accumulation via manure injection. And then another hypothesis that we wanted to investigate was, well, because we're conserving that nitrogen by injecting, are we enhancing any kind of nitrogen uptake to the crop? Is there going to be a difference in yield, or is there going to be a difference in another metric? And so we looked at the late season stock nitrate test, which when you take that 8-inch lower portion of the corn stalk at harvest time and have it analyzed, you can see, okay, how much nitrogen did my corn plant have at harvest? And the injected plots did great. So we had more than enough nitrogen available for the corn, and broadcast plots had much less. And so that was kind of exciting and promising. We thought, oh, well, we saw a difference. Again, nitrate and part per million on the y-axis, but basically, oh, so the corn plant had a lot more left in its stock reserves. Maybe we'll see a yield difference. But again, unfortunately, this is our corn silage yields in dry tons per hectare. And in 2012 and 2013, we didn't see any treatment differences. Again, like there's a lot more variables to consider when it comes to our yields as well. So some of our plots were really shallow, didn't have as great a rooting depth. It was kind of droughty during the growing season. There's so many other variables that are going into yield than just manure and just nitrogen. But it was interesting that we saw one indication of conservation of nitrogen in the corn. And so with all of this, I was able to calculate what I was calling manure year budget. So from January 2012 to September 2012, we had one manure application, and that was in the spring, and roughly 200 kilograms per hectare of nitrogen was being applied, and the bottom two charts are how that percent of N applied broke down. So for broadcast plots, the purple chunk is all volatilization, so you're going to have a huge amount of volatilization from broadcast. The green is crop uptake, the largest portion of both of the budgets, inject and broadcast. And then orange is unaccounted. And so in the injection budget, there was a larger chunk of unaccounted nitrogen, harder to measure. Where was that savings in nitrogen going? And so we still weren't able to do a good job of trying to capture that, but it was interesting to kind of break them down and see where the differences lie. When we did that with our next manure budget, it was October 2012 to September 2013 to capture a fall and spring manure application. So we had about double the amount of N with those nitrogen applied with those two applications. And what was interesting in these two budgets, we had double the measurements as well, because we had spring and fall volatilization and nitrous oxide. So those two parts were double the previous budget. But the unaccounted for portion for the broadcast plots was actually a little larger than inject, but it seems like a little bit more similar. And again, ammonia volatilization is a large piece of the pie for plots receiving broadcast manure. And so to kind of bring all of this together in an applied fashion, I used the integrated farm system model, which is a tool provided by Dr. Al Rotz with the USDA-ARS Research Service. And so you can track everything on your farm, from your cows to what you're putting on your land to what you're growing, harvest. Everything that you see on this cartoon is something that you can manipulate and something that you can use to model various treatments. And so I used that to look at manure injection and surface application, but also look at storage, because in the real world, it's a lot harder to manipulate something like your dairy manure storage. And so in this model, it was an added level that I was able to include. And so the rationale behind this was that with legislation and with a lot of pressure on ag in the Chesapeake Bay, there's thought of, oh, well, farmers should only be applying manure one time per year. They shouldn't be going out in the fall and in the spring or things like that. There's a lot of talk that happens. So we wanted to simulate, well, if a farmer had 12 months of storage, which is very unreasonable, but if they did, what would it look like with these two different treatments? So on one end of the spectrum, we had a daily haul farm with no storage, and then a 6-month operation, which is a little bit more common, and then 12 months of storage. And so we looked, the model can simulate anything, and any of these variables that I have up here, so environmental, looking at nitrogen leaching, across the board, we see that it decreases a bit with the 6 months of storage, and then it decreases even more with 12 months of storage. And that's just because it's simulating that you're applying one time. When you're looking at the emissions, it does a pretty good job modeling ammonia volatilization. And then when you look at the whole farm nitrogen use efficiency, you can see your efficiency significantly goes up with 12 months of storage. But when you layer in the economics, so I worked with a state engineer to come up with an estimate of what a 12-month storage facility would cost. It was about $230,000. It's a big chunk of change. 6 months storage would maybe cost around $140,000. And so what's your net return? Well, a daily haul operation under these circumstances versus 6 months of storage and 12 months, basically the bottom line was the happy medium, if you want to think about your environmental, weigh your environmental costs with your economics, would be something like a 6-month storage situation and injection of manure. And so this was an interesting exercise to do, considering there's a lot of talk about when people apply their manure and how, and I wanted to scale up the research. So in conclusion, there's a large trade-off with gas emissions, as one would expect. In terms of ammonia volatilization and nitrous oxide, there's a huge savings in nitrogen if you incorporate. And then there's preliminary indicators of treatment differences. So it was promising that we saw greater nitrogen reserves in the corn silage at the end of the growing season as compared to a broadcast treatment. There's potential to not need side dress nitrogen in that situation. So maybe you remove a fertilizer application if you're injecting your manure. And then combining manure storage with injection was the best environmental and economic option. So with that, I'll take any questions, comments, move on. Yes?
I have a question. You're doing this research in Pennsylvania, is that right?
I did, yeah.
So one of the things that they're trying to do now is put cover crops out there. So why wasn't cover crops part of this study?
Cover crops were part of this study. It's not something that I talk about in this. It wasn't something that we were measuring, but in between corn silage, we had either ryegrass or clover.
Okay, but
But it was killed and planted into. It wasn't removed for.
So did you apply manure to the cover crops as it was
No.
growing? So that's a very common practice now, and one of the things that's going on in Pennsylvania within the last 7 years, they've had an improvement in water quality in the Chesapeake Bay of 40%. I mean, that's 40%. I should say they've reached 40% attainment on water quality, and a lot of those farmers there are broadcasting manure in the winter to their cover crops because they got a cover crop up about this
That's
tall.
established.
So I'm wondering why there isn't more research going that way.
It's a good question.
Yes.
I am now
It
working
is
in
a very
Ohio.
good question.
Yeah. Do you
In one of your first
want the
slides, you
microphone?
said nutrient loading. In one of your first slides, you had nutrient loading broke down as 18% animal and 19% commercial fertilizers. Was that nitrogen only,
Nitrogen.
not a phosphorus?
That's
Just
not the
not
phosphorus
total
number
loading,
statement?
just nitrogen?
Just nitrogen,
Okay.
yeah. Okay. Good?
Quick. I missed what your total volume. I'm over here.
Oh, sorry.
I got your nitrogen in your manure application. What was the total volume in your application?
We're like gallons per acre,
Like-
or no?
Gallons per acre, yes.
Yeah, we were applying roughly 6,000.
6,000, okay.
And what kind of manure?
Dairy slurry.
Okay, thanks everyone. We are heading into a break. Join us after the break at 9:50. If you can't get enough of precision nutrient management, come back here for 3 more excellent presentations at 9:50.